should just record. So maybe I'll just yeah, maybe I'll just say congruence is, just to give it a little bit. Okay, congruence is mod p. Yes. So Aparna, so we are trying to, you are saying that you have a way to prove this. Okay, so let's see. 7. So p is 7 for you. Go on. Multiples or okay, multiples 4 into 2. Huh? Huh, okay. You get all the numbers from 1 to 6. Yes. So just let's just calculate all of this so that everybody could just check the calculations. Good practice. 4 times 5 is how much? 6. Last one. What is this? 3. Good. Yeah, Pragadish, do you follow this notation? Yeah, because it's been 1 week, so I'm just okay. Good. So we're taking the remainders modulus of that. Okay. Okay, Aparna. So then go on. Oh God. Okay, that is so good. Yes, that is wonderful. Multiply all the equations. Okay. Nice. So you multiply. This is something which we actually proved last time, and Aparna has applied it. Either way, but it's very interesting, right? That you just multiply all the equations. You understand what I'm saying, right? You multiply these and multiply these, and we know that this can be done. We have proved it for 2 equations, and so obviously for 3, 2 at a time, and so on. So you multiply all the equations. Okay, we'll see. But first, I want other people to raise questions if there are any in this, because this is do you think there's something that needs to be explained or something which is not correct? First, let's check that. Because this is very, very interesting. So till here, I suppose, yeah, Ishana and Pragdish, is it okay? Just multiplying all the equations. Right. And this is something, this is wonderful, right? I mean, yeah, so what is this? Like, how is this? I mean, it's a very strange thing, right? Okay, now the next thing is, so what is, okay, Aparna, tell us the next step precisely. So these, you are saying, okay, so these two are the same thing. So that we know, because these two are both multiplication from numbers from 1 to 6, 6 factorial, or just the value itself. These are 720. But then why can we cancel 720? That is something that we should explain. Why can we cancel 720? That is something that we have to explain, so that we learn these formal things also. 720 and 7 are co-prime. Okay. Yeah. So can okay. So can you tell us more details then? Just think, try to frame the details. So Nagesh, so this is something very interesting that we have come to. So last time, I don't know if you, last time we had done this, that we had kind of got this through observations and so on, that given any number A, if you raise it to the power P minus 1, right, then the remainder that it leaves is 1 when it is divided by P. Given that A is not equal to P, or not a multiple of P, let's say, same thing. This is something that we had seen this from different ways, but we do not know how to prove this. And in fact, I was thinking the proof is difficult. Okay, but Aparna has suggested this technique. Yes, so Aparna suggested this technique through this example. At least this is just an example. Now we will see if we can make this work in general. Is that you start with this 4 and you take its various multiples. But when you see the remainders, you get all the remainders, in the sense that you get all the 6 remainders. Okay. And then you multiply these equations. And this is something that we had actually proved last time, that you can multiply 2 congruence equations and 3 congruence equations. Okay. So we get this. And so we get this. And then we are saying that we can cancel 720 and get this. And that will be the final thing. Okay. But then why can we cancel? We would like to have a more first principles explanation. Then we would have proved for the first non-trivial theorem of number theory. This is called Fermat's Little theorem. Okay. I mean, okay, for this. Yes. Huh? Yeah, but then you have to explain, right? You have to explain why this is true. So let's try to think. Yeah, Ishana, do you have any ideas? Like, just use the meaning of it. Okay. So, but we had seen last time that you cannot always cancel. That is agreed. Yeah, or sometime earlier. Okay, maybe I shouldn't recall so many things, not important, but we cannot always cancel. Okay. So what is the meaning of this? Yeah. What is the meaning of this? This means that n divides AC minus BC. That is just the meaning of it. So try using that. Okay. Think. This is the one thing that one has to think and explain. Yes. Yeah. If C and N are co-prime, it means that N has no prime factors with C. Right. So then it's okay to say, it's perfectly fine to say that N has to divide A minus B. But then that is exactly what this means, right? That A and B are congruent. A and B leave the same remainder when divided by N. That's why A minus B is divisible by N, because the remainders cancel. If the remainders did not cancel, it would not divide. So then, please don't rush it. See if this is fine. Maybe we can take a few simple examples. And also see when you cannot cancel and so on, because it's not always true that you can cancel. For example, 24 is 24 is congruent to 15 mod 3. Right? Is that right? This is true, right? Yeah. But then can you cancel the 3? Can you, can you write this as 8 and so 3 8 and 3 5? But it does work in this case. So then what is the, so can we always cancel? You see, I am able to cancel 3 and this is true. But then can anybody give an example where it does not work, but you cannot cancel? Please think of some example. I mean, this seems to be a coincidence. I don't know. Yeah. Just take any example, right? Just, I think if you take any example, it should work. I mean, just don't take 24, take 27, right? Easy. You see, you get a wrong thing, right? If you cancel the 3 nines are 27 and 5 threes are 15, you get 9 congruent to 5 mod 3, which is not correct. Okay. So you can't always cancel. Okay, that is not correct. But the common thing, if it's co-prime to C, then you can cancel because it doesn't create any new divisibility. All right, so there are more things there, but we can cancel the 720 and we can say this. Okay. So now the task is to make this kind of thing work for other numbers. Is that right? Yeah. We would like to make this thing work, or let's just replace for a minute, replace 7 with a P. Let's keep the 4 as it is and replace the 7 with a P and see if we can make it work. Okay, and please stop me if there is anything you want to ask. Okay, don't leave it for later. If we replace the 7 by P, then how do we carry forward this reason? What are the key things that we would have to go for? Obviously, we would go till P minus 1. So, what was the main thing that happened? Like, what was the first good thing that happened in the case for 4 and 7? Yeah, what was the first good thing that had happened when we took from 4? We took all the multiples, 4 times 1, 4 times 2 till 4 times 6. Yes, exactly. Right. That's the thing, right? That you get all the remainders. Here also, we would like to say that whatever remainders you are getting, you will get all the remainders. Yeah. So we want to say, so the claim is, what should the claim be? You can write it in words, but I'm just saying the same thing in just notations. We would like to say that this set, assuming you're writing the remainders in the standard way from 1 to P minus 1, this set is the same as this. That is just one way to say the thing, that you get all the remainders. Yeah. So why is it that you get all the remainders, and what does it mean? Okay, let's just forget what does it mean. Why do we get all the remainders? That is what we need to show, that you get all remainders. it's kind of, it seems correct, right? That you, when you take a prime number and and number like 4, or in fact, it seems like any number, you will get all remainders. Some sort of a cycle, something. Okay, I mean, yeah, but there is a little, can you bridge the, and that is the final thing that we use. Okay, that's one way. But okay, so it is true. So let me just state what you said. So you're saying that, yeah, obviously that P divides 4P, yeah, but P does not divide 4 times K whenever K is less than P. That's what you're saying. But then why does this, if you dig more into it, now why does this imply that you get all distinct remainders? Like 4 times 1, 4 times 2, 4 times 3. Then why are they all different? Like we are basically, I mean, we are basically saying that all these are different, right? Does everybody agree with this? As soon as we show that they're all different, we are done. I mean, in the sense that as soon as we show that all these remainders are different, then they have to cover everything from 1 to P minus 1. Because there are P minus 1 numbers, right? From 1 to P minus 1, and they're all different, then they are the set 1 to P minus 1. Right. Yeah. So what I'm trying to say is that any Ri is not equal to Rj. Means all the Ri's are distinct. That's what all we want to show actually. We don't have to explicitly show that you get all the remainders. That will follow. Once you show that these are all the remainders are different, then automatically you will get all the remainders because they are from 1 to P minus 1. Yeah, this can be a little confusing, but these are these, think of these, not these, but as the remainders that they leave. So from 1 to P minus 1. Hey, first, is that thing clear? That it's enough to show that they're all different. Yes. And now Nagesh is saying that that follows from the fact that nothing before 4P, is divisible by P, but then there is a gap there which one has to fill. Yeah. Nagesh, do you see that there is something that you have to explain in between? Right? I mean, I know it's maybe obvious, sometimes it's obvious, but one has to explain that. So P, it's clear that P doesn't divide any of these, right? It's clear that none of these are 0. Just what Nagesh has said directly implies that none of these are 0, right? So none of Ri are 0. Or is 0 is the right way, but yeah. Or whatever, it doesn't matter. This is clear, right? Because that's what is the statement, right? That P cannot divide anything. Obviously, right? 4 times something less than P, P cannot divide it because P is co-prime with 4. That is the key, right? P is co-prime with 4. And in fact, with anything that is less than P. So none of them are 0. That is clear, but we want to show that they are all different. Huh? Yes. So yeah, if you take 4, but then that's what we're trying to prove, right? That when you multiply 4 with all of them, then why is it that none of them become Like obviously none of them become 0, but why is it that none of them repeat? Yeah, they're sort of obvious in the sense that, yeah, now it's looks more and more correct that, yeah, none of them are 0, so no two should be equal. But okay, then just prove it by contradiction, right? Just if Ri is equal to Rj, what does it mean? It just means that 4 times I is congruent to 4 times j modulo 7 modulo p. That's what Ri is, right? Ri is the remainder when 4i is divided by p, and Rj is the remainder when. Yeah. But this implies that p divides 4 times I minus j. But then that's not possible, right? That's what we have said. Or this is just not possible. You just see is as it is here. Because I remember I and j are less than p minus 1, less than equal to p minus 1, right? Not possible unless I is equal to j, right? Yeah, but one has to say this. Yeah, I know. I mean, this kind of thing always happens whenever you have to show that a set of things is distinct. This is general feature in any place where you have a 0, in any place where you have have an origin. Yeah, you can translate these questions to the origin. So a question like show that all the outputs are distinct, or the show that the function is injective, if you know what that means, right? All the outputs are distinct, or things like that, or the period is this much, to show these things, one can translate these statements to origin and try to show that, 0 is not in the output other than when the input is 0, something like that, right? So that's the kind of thing this is. But but at this level one has to say it, otherwise you won't even know if you know it. Okay. And then you'll end up making the same explanation in a wrong place, so where it is not true. Yeah, so go over this for a couple of minutes. I think this is a new thing which we have done, so go over this. I will suggest that you take another prime, and take another number and check if you get all the remainders. Okay, and just go over this. Then I'll go into a few more things about this. This is something very interesting. And also, this is very important. Fermat's Little theorem is the beginning. Okay. Yeah. Just go over this. Yes. So please say, is there anything Yes. So basically the last part we are going by contradiction, right? So it's clear that we are trying to show that all the remainders are distinct, right? And we know that none of the remainders are zero. That's clear. But now to show that all the remainders are distinct, how do you show such a thing? You assume that two of them are same, right? That's the way to show. So if you assume that two of them are same, then what happens? Then it means that there is a 4i and 4j, which leaves the same remainder when divided by p, right? But what does that mean? It means that p divides 4 times I minus j, right? But that means that I equals to j. Yeah, because obviously p will not divide 4 because p is a prime. Okay, I mean, I should say that p is a prime bigger than 4. Okay, yes, that has to be said. That we are assuming, we are saying that you take, we had said that a is less than p. Yeah. Okay. Yeah. Let's take a few more examples. Just saying it like this is not, because this is really maybe the most important thing in elementary number theory to begin with is that when you, okay, one special case of this which we are seeing now is that when you start with a number, okay, let's say start with 4, right? When you start with 4 and you take these multiples till 4 times p minus 1, you get all distinct remainders. Yeah. When you take the remainders of these divided by p, these are all distinct. And I will try to show you today why this is the main thing. Though this is not what I had in mind when I was thinking about it, but since it has come up, this is the main thing. This is the first main thing you can say. Okay. And yeah, so, but before that, let's just work out a few more examples. Okay, so let's take p equal to, let's keep 4 as it is, and let's take p equal to 11. And so you guys tell me the sequence of remainders. Yeah, 4, and so 4 times 2, what do you get? You get 8. 4 times 3 is what? Okay, maybe I'll just write it here, right? $11, or let's just say, okay, so I can just keep this. Yeah, so someone say, yeah, what are the remainders that you get in the order? So p is equal to 11. So we get 1, we get 4, we get 8, then we get 1, right? 12 is 1, right? And so how much is 6? Yeah, 5, yeah, and 20 is 9, and right, 2, yeah. Ten, 3, and 7. Very good. You see, and you can see that you get all the remainders, right? Okay, so I think I've written something wrong. It's 1, not 11. Yeah. And you also see that there was something which was very important earlier, very important earlier, was to, for a given number like 4, to find a number x which leaves a remainder 1. Yeah, it is important, not because I'm saying, you can just think that it is important, right? To find an inverse of something in that language, in the new language that you set up, having an inverse is important. Even if you don't recall where it was important, that's a different thing. But this is something that should be important, right? It seems, okay, if it turns out to be no, then fine. But it's not important, it's fine. But it seems like an interesting thing. And this was something that we were looking after, right? We were, in the sense, we had that algorithm which found the inverse. It proved that such a x exists. You guys agree, right? We had converted this into equations and so on, if you remember. But it's naturally important, right? What was the thing? Given any a, we were trying to find a x which leaves a remainder 1, provided a and n were co-prime, remember. Okay, and whenever they were co-prime, we went a long way and we showed that it exists. Such a one comes. Now, but for primes, we are getting the 1. And have we proved that you will always get 1 as a remainder somewhere? Yes, because that's what we have proved, that you get all remainders. Right. And in fact, proving that you get 1 as a remainder means you will get all remainders. See, that's also true. Okay, so that theorem which we had, now this is not very important, but that theorem which we had proved, where we showed that 4 times x is 1 mod p, that theorem can also be used to prove that you get all distinct remainders. Because if you're getting 1 as a remainder, you will get all remainders, just x. So then 2x will give you 2, 3x will give you 3, 4x will give you 4. And then so x, 2x, 3x, again, I mean, that when you reduce, you get 1, 2, 3. I mean, yeah, so there is something, some a little bit of a loop is there. But anyways, yeah. But it's, actually, there's a little bit of a, but fine. You can see these are connected statements roughly, but I don't want to go from that direction here, but from this elegant direction to there. Okay. But first, we are understanding that this is true statement. It's a true statement. It is not surprising statement. Okay. 4 is co-prime, right? So you have to multiply, you have to consider all multiples, you have to consider multiples till p, right? To get 0. And in the meantime, you will not repeat, otherwise you get 0, right? Or either ways. Yeah, so the remainders don't repeat, and so you get everything. That is a statement. Okay. So let's give it a name. So now I will make a statement which you guys can think about. This is very similar to what, now I'll remove primes. I will try to do something more general. Okay. In the sense that given that E and N are co-prime, GCD is 1. Okay. I mean, let's just write 4 here for a minute. One step at a time. Okay, 4 is co-prime to N. Then also you get all distinct remainders. Should not come as a surprise, because that's all we used about P there last time. Or we, yeah, right. So this is a complete, this is what is called a complete residue system. These are residues, right? These are residues when divided by N. These are the remainders, or residues is the more general term, because they don't want to use the word remainder. It's already used since centuries maybe, and that's why they don't use. Anyways, yeah, the point is they call it residues. But yeah, so either way, this is a complete. Okay. But we'll just say in our own simple term, just in the way that I've said earlier, I'll just say like this only. But if you want to, when you read about it and so on, the complete residue system is the word. Okay. And it's a sensible word, I suppose, very sensible word. You get all the distinct remainders from 1 to N. So, I mean, okay, maybe I should say 0 to N minus 1, or what? Let me say 0 to N minus 1. Right? That's better. I'm writing 0 also, it's fine, right? We're considering 0 also, it's okay. This is the same set. I mean, if you consider the remainders, up to remainders, I mean, maybe I should say congruence modulo 4, but that we are understanding, that's the language we are using throughout. So this is the statement. Yeah, we have proved it for 4 and P, but if you go and look at the proof, there is really nothing about P. It's just that P doesn't divide 4. Or not just that, P has no factors with 4. That's the important thing. n has no factors with 4. That's all. This is the most important. You could say from here you could read the rest of most of elementary number theory, at least the multiplicative things on your own. Most of it, at least. Yes, this is the statement. Yeah. And this is emphasized in Niven and Zuckerman's book, but it has other things which is a little difficult to penetrate in the beginning. But if you can make it through there, then this is what that book emphasizes on. Burton, I don't remember actually. But for any A, it is true. No, there's nothing special about 4 again. Or is this yeah, just see if this is correct, or if you think there is something in this which is yeah. Huh. Yes. Mm, so you take the first 5 multiples. So you take okay, so 4. 4 times 2 is 8. No, but 4 times 2 is 8. So that's 3. Are you taking powers or? Huh? Oh yeah, yes. That's what you said. You said 0 to 4. I thought 0, 2, and 4. Okay. Yeah. So that's why I was a little. Yeah. So you see, you get all the things, right? And so for any A which is co-prime to n, you will get everything. And there's the same thing. Yeah, you can check it. We have also proved it. But basically, all is a distinct is what all you need. They're distinct is all you need. Okay. Yeah. So this has one major implication which we have proved today, is that if you put n equal to p, if n becomes a prime number, yeah, then the same method which we did right at the beginning of the class will give you that a to the p minus 1 leaves a remainder of 1 when divided by p. It should, right? There is no other way. Yeah. Yeah. Extremely elegant proof. So already you can see that this fact seems to be nothing tricky, nothing very strange, but somehow very crucial. Okay. And but let's just work just to cite the proof. So you have 1 leaves a remainder of 1 when divided by no. So a leave the remainder a. Then you do a times 2. No. So what am I saying? Yes, a leaves the remainder a times 2. So we have to write the remainders, right? Yeah. So let me just, I mean, a is already a, but still, let's just write R1. It's a, but I'm just writing it R1, you know. So you basically, it's the same thing, same proof. So you get all the remainders. And so on, right? You get a to p minus 1, you get rp minus 1, mod p. Exact same thing. You multiply all the equations, you get a to the p minus 1, and you get here p minus 1 factorial, right? And here you get r1 to rp minus 1, but we know that that's the same set as 1 to p minus 1. That is the same. You get all the distinct remainders. That's the thing. You get all the distinct remainders. Yeah. And so that's p minus 1 factorial. And then the crucial now here is where we are using the fact that this is a prime. P minus 1 factorial and p no common factors. This is crucial here, that we are using the fact that it's a prime. Yeah, but then that's a simple thing, right? After that step, it's a simple thing that you can cancel. That's just a small thing, right? So here we have p minus 1. Yeah. And that gives you, okay. And that's your Fermat's Little theorem. Obviously, when Fermat proved it, they didn't have this language. And that's why it was a big theorem that time. It took some big proof to do it. Okay. Sometimes that proof is you can find in some places. I can say that, but let's not. And understand this crucial idea. That is the thing. So we already see one pretty wonderful outcome of this, right? What is the other quite important outcome? Is that there exists a x such that ax is congruent to 1 mod n. I mean, if you're getting all the remainders, you better get a 1 also, right? From some multiple. Yeah. So this is called there exists. You can just write there exists. It doesn't matter. Okay. I mean, so these are just the beginning. These are the two things. These are the two things that we have. Yeah. So yes. So so what do I want to say then from here? What more do I want to say? Yeah. So the main thing that I wanted to say is that if you look at, so what else this means? Yeah, it means that, see, if you think about this thing, let's see, let me use a notation, and from you can extrapolate from the notation itself what I'm going to say. Because notations are so powerful. What I'm saying you start with A and you take the thing that you can generate from A additively. A and whatever you can generate from A additively. What do you mean by additively? You take A plus A. That's what this set is, right? A plus A. It's not A square. That is a different thing, which we had kind of seen a little bit last time. That has even more mysterious things, properties, right? But this thing is that you have A plus A plus A plus A. That's what this is. I mean, we are using multiplication. That's a for our own convenience, but that's what it is. It is A plus A. Yeah. So basically, additively, what all you can generate. Yeah, that's all it is. So maybe I can just write using A and addition, what all you can get is that set. Obviously, the operation is you add and then you take the remainders. If you need to, you take remainder. If the number becomes more than n, then you take, that's something that we've been repeatedly doing. Okay. So that's understood. Yeah. I mean, otherwise you will get everything, right? You A and then you again get A times. I mean, if you just take, you get this thing called arithmetic progression, right? Which you know, obviously, or I don't know. So if you've not heard the term, it's fine. Doesn't matter. These are much deeper things maybe. So arithmetic progression is just this, and just something that grows at the same difference, increases by the same amount. Yeah, you get this, but obviously we are only interested in remainder, so we stop here, right? And here also, so the number may become more. We will take the remainder and bring it down. But we are sure that you don't have to go beyond this. And that is sure. Yeah, that is certain. To find all the remainders. I mean, after this, it just repeats, right? I mean, n plus 1a is the same thing as a, right? As far as much as we are interested. Yeah. So what was I going to say? So I'm trying to say that starting with a, if you generate this set additively, this is called additive subgroup. or additive group generated by, yeah, just the whatever you can get from A additively. That is what that means. But what are we saying? We are saying you get everything, right? We are saying you get everything. So we are saying that A is a generator. Okay, that's of what? Of Z n, yeah, meaning that thing, right? Where you do addition modulo n. Under what? Under addition, not under multiplication. That was something which we had seen last time, but this is just under addition. A is a generator. So, okay, so just to make this point more clear, 1 is a generator, right? Because if you start with 1, 1 plus 1, 1 plus 1 plus 1, just what we were doing powered that day, this is just addition. It's even simpler, you can say. Yeah? I mean, you certainly get everything. 1 is certainly a generator, but what else is a generator? A is a generator. Which A? Any A that is co-prime to N is a generator. It will give you the entire thing. You can start from there and you can be sure. So it kind of acts like a 1. It's kind of like a 1. Or in the sense that it's similar to 1 in the sense that it has an inverse, right? Right. So please see if there is anything you want to scale, right? For a, yeah. No, this much will be all, these will be true. So here there's no need to, so the point is that this one, the first statement, does this need the fact that N is a prime? No, right? If you, yeah, it doesn't need the fact that N is a prime, right? That is all you need is that is co-prime and you can work out the same proof, but let's just have a look at an example that it should, because of several other uses as, if you take 3 and 8, so you take A equal to 3 and you take N equal to 8. You see, 8 is certainly not prime. It's the power of a prime, but you can take anything. Huh? But it has to be co-prime. Okay? 3 and 8 are co-prime. Then you can see you take 3, you take 6, you take. So let's just write all the multiples first. What's the next one? 21, 24. Right. Compute the remainders. 1. So you already have a 1. The moment you have a 1, you are done. You will get everything. Okay, but work it out. There's no need to conclude, like no, you can just work it out. 2, 5 and 0. You get everything in some mysterious permutation. You get everything. Yeah. Okay, so that's the thing. And the fact that A is a generator is the elegant way to put it, because the moment you say A is a generator, it means that using A, after some additions you get 1. So this implies this, right? And obviously once you get 1, you get everything. This also will imply this for P is a prime. That's because that's just the same statement. This is just the same statement. I mean, this is all is the same. Okay, not this one, not this one. Okay, this is a little, but the point is that one doesn't have to know at every detail. But the point is that here is that this thing implies all this simply. Okay. So now, what should be the next question? Does any questions arise? Do any questions arise in your mind? Just think if you have any questions. Certainly, I mean, this result, if you just know this result itself is very useful. Okay, this is used in countless number of problems. we will devote maybe a class to applications of it, when especially in computing remainders and in combination with Chinese remainder theorem, and this goes on. But from here, this discussion, what questions come to your mind? So if you get 1, then you know that you will also get 2. If so can you say your state question again? In what way is A a generator? Yeah, okay, yeah. So that's a good question. So if A can generate 1, okay. So if A times X gives you 1, right? Then you know that A becomes a generator, right? Because A times 2X will give you 2, right? A times 3X, it has to give you 3. And then you can see that you get all the remainders. And one doesn't have to worry about these X's too much, because I mean, if they go outside, you can pull it back in. It won't change the remainder. If it goes outside n, you can just take the remainder of that. But you do get every remainder by taking multiples of A. So is that so no, but that's okay. So that is we are getting because X and 2X are in a strange order. That's why it's reordering this remainders. X and 2X are not 1, 2, 3, right? This 3X could be something else, something lesser than 2X actually, right? In a sense, let's take a small example. So yeah, we can take this 3 and 8 only, right? So what is the inverse of 3? Yeah, 3 itself, right? I mean, it turns out that in this case, it's 3 itself. It's not always true. Don't assume that. So 3, so this X equal to 3, right? So 3 times 3 gives you 1. Yeah, it's a good question in the sense that, yeah, why are we now the remainders are getting ordered? And that's a good, this is a good way to order the remainders, which appear in a mysterious order, right? But it gets reordered by this. But then you see, when you take 3 times 2, you will certainly get 2, no question about that, right? When you take 3 times, when you take 3 times 3, when you take 3 times, wait, yeah, when you take 3 times 3, you get 3. So how am I getting these things? You can just think that I am multiplying this equation by 3. You can think of it like that, right? And yeah, and so when you multiply it by 4, you get 4. Now you will say the remainders are getting ordered, but then if you take this in the previous language, then this part is unordered because it is 3 times 6, not 3 times 4, or not 3 times 2, right? 3 times 3 and then 3 times 6. So that is where it's getting, it's doing, and then here it is. And this is 9, which is actually 1, 3 times 1. And this is 3 times is 12, that's 4, and so on. You can, whatever, you can work it out. You see, so this is the thing. But if you get 1, then you get everything, because obviously we know additively, I mean, from 1 you get everything, right? That's the point. But yeah, it's good to, because it seems strange that it gets ordered, but it does work. Yeah. Okay. Okay. So we have found the one power of A, which gives you remainder 1 when divided by P, right? that is a very good thing out of all these things. Yeah. But then a really interesting question, especially those who like combinatorics, is how many generators? This is a question that combinatorics people ask. And obviously, I'm just saying it like this in a way, but this is important theorem in your syllabus or whatever you want to call it. Yeah. How many? They won't say it like this usually. Usually, they say it in many books. But yeah, how many generators is the question? I mean, it's okay, right? Good question, right? How many generators? Yeah. For a number n, can you find a formula for how many generators? What is all this? I mean, I'm just asking how many numbers are co-prime to n? Right? Yeah. That's all this question is, right? Given n, how many numbers less than n, otherwise they're infinite. I mean, obviously interested in less than n, and co-prime to n. This is the same question, but just in the language of how many generators. It has, one way, and this other is just interesting on its own. This is also interesting enough, I will say, maybe. Both are, yeah, same questions. Both are same questions, and just the question is, how many numbers less than n are co-prime to n? Have you guys ever thought about it? No, that's not correct. 4 and 6 is the standard. Yeah. So it's not a prime, obviously. Obviously, I know you're not saying it's a prime, but yeah, 4 and 6. I mean, so yeah, in the sense that 4 and 6, right? 4 is not a factor of 6, but they are also not co-prime. Yeah. So yeah, so that what you are asking, what you are saying is the number of divisors, which is another interesting question. How many divisors are there for a number n? And that can be done by one of the methods we discussed about computing LCM. So, but anyways, how many numbers less than n are co-prime to n? This is something which you guys should think about. Okay. And maybe you cannot answer this, but you can try to read about it. But the question, according to my the way I would like you to try, it will be good, is first you take n equal to p. So I think this you can answer immediately. For n equal to p, what is the answer? If n is a prime, then how many numbers less than n are co-prime? How many numbers less than p are co-prime to p? What someone said p minus 1 is right. Ishana, what did you say? Okay. P minus 1, right? P minus 1 is correct. Yeah. Obviously, I mean, that's it. But then what I want you guys to try is n equal to power of p. If you take enough examples, you will get an answer because there is a pattern. Obviously, if you see more than just that pattern, that's very good. But just try for powers of prime. Take p square. Huh? It's not difficult. Try to see. So somewhat like what Aparna has said would work, I suppose, because p square is also, at least for p square, it will certainly work. Yeah. So co-prime to, yeah, you can just think first. Yeah. No, again, there will be a similar problem, right? Because let me tell you, let me say an example. So 1 minute. Yeah, so it's very simple. You can just take a simple example. So you can take 9 and 21, right? You see, so 9 is not a divisor of 21, but 9 will obviously not generate. Or simply put, 9 is not co-prime to 21. You can see there is a weight on the factors, right? That you can always fool around with. So yeah. Yeah, so, but this kind of reasoning which you are saying, that's why I gave this example, might work for p to the power k. Yeah, you can kind of we feel it. So it might work for p to the power k. Think about it. Take your time. They don't have to do one. I'm not trying to do this now. Not needed to do it now. This is something that's a good question. It has come from what we have done, and it's a crucial question. This will later lead to something, which and it will connect back with all this. But this is the thing. Okay? So fine. You should note this down. Yeah, just if you want to try this. How many of them are co-prime to n? Let's say we don't know the answer, okay? But let's say that assume that k numbers less than n are co-prime to n. But this doesn't sound like a good way to say, right? K, but the k should depend on n, right? So we would just put that in. So instead of k, let me just say f of n. In a sense that it depends on n. It's a number, yeah, fn many numbers less than n which are co-prime to n. We don't know what it is, but we know that there is some number, right? I mean, is something, some number, right? That's some number less than n. It's the number itself is less than n. Okay. Right. And yeah, anyways, yeah. So let's say that these are the many numbers. So what we are saying is that we let's say have a1, a2, afn. These many numbers are co-prime to n. Okay, are co-prime. I mean, these numbers are co-prime to n, and they are less than n. Less than n. Let me not say less than n anymore. Just co-prime. Okay. So, for example, don't worry, it's not getting too abstract. It won't get too abstract because we are trying to do something similar to this here. Okay, so I won't take it in some other way, just in the context. So what to get an example, if you take, for example, the number 10, then which numbers do you get? You get 1. 1 is always there, right? 3, 7, 9, 4 numbers. So for 10, it's 4. Yeah, these 4 numbers. Yeah, so let's actually do that. Let's actually take some number. Let's take 15, for example, and then you can write down the numbers, just like we did earlier, right? You can start with 1 and what's the other things? 2, 4, 7, 8, 11, 13, 14. For 15, it is these many numbers. And these are the numbers. Okay. So earlier we had taken a equal to 4, right? But p was a prime. Now we are trying to explore something similar. Okay. And what are we going to take? Let's take 4 again. Let's see, if you take the number 4 and you consider all the, let's consider this 4 again. Okay. Take the number 4 and you consider all the multiples once again till 14. Again, you agree that we will get all the distinct remainders. Yeah, right. So we get all the distinct remainders. And again, do we multiply? Yeah, let's see. If we multiply, then what do we get? 4 to the power 14. And here we get 14 factorial. Here also we get 14 factorial, and here we get 15. But then can we cancel? No, right? We just cannot cancel these two things. Because now, I mean, in general, we cannot, right? Sometimes we might be able to, but in general, we cannot. Because this 14 factorial divides, I mean, 15 divides the 14 factorial. I mean, 15 and 14 factorial are co-prime. In fact, it divides, but are not co-prime, right? So you cannot just cancel. I mean, sometimes it might be correct, but in a general thing, it will not be, it's not correct always, okay? So then this method stops here. Or what is stopping it is what one must think. So just a little bit fast forward I'm doing and saying, see, the point that is stopping it, what is stopping you is because you're multiplying it by all remainders. You are taking those remainders which are not co-prime to 15, and they are becoming a problem for you later on. All right. We are taking all those remainders also which are not co-prime to 15. And that is where the problem is coming. So we should only take those remainders which are co-prime to 15 and work in that little space. Okay. Because this 14 factorial is coming, right? But if we would have not taken 3 as a multiple, and we would not taken the multiple as 3 or 5, then let's see. Yeah. So now we know that starting with 4, you get all the multiples. It's right. If you take all multiples, you get all the remainders. That's very good. But it doesn't work later for our this kind of a to the power kind of thing. For P, it worked because you know why. Everything was co-prime. Now what we will do is we'll take, and we will only take 4. We'll take 4, which is co-prime to begin with. We have to obviously start with a co-prime number, but we will only take multiples which are co-prime. And now we will see what we get. Okay. What should be the next multiple we take? 4 itself. Yeah. And what's the next multiple by 7? We won't take multiple by 6 because that's the problem that is creating a problem later, right? We will now quickly calculate the remainders for me. 8 will give you 8. 16 is giving you 1. And the next ones, 13, 2, 14. And again, something interesting is happening, right? Again, you're back to that same set. So it means that we're certainly doing something good. We came here avoiding something, but it doesn't mean that it will work later, but now it should work. We're doing something good. I mean, this is math is telling you that it's go ahead, right? This is the thing. So if you do 52, 13 for the 52, 7, yeah. And then it should be 11, yeah. Hopefully, wait, is it, no, is it correct? 14 fours, no, what is 14 fours, how much? It's 56, 11. I was saying, I think 64. Yeah, 16 fours are 64, right? Good. You see, you get everything. Right? So even this, so there is a permutation. Yeah, you take 1 to n minus 1, or you take 1 to 15 and you multiply with 4, you get a permutation. But when you pick these co-prime things and multiply with 4, you get a permutation in that only. Okay, so they don't mix. And there is a further demarcations can be made, what mixes and what not mixes and other things. But these things are in their own thing, on their own world, they're getting permuted. Okay. So now what does it mean? I mean, now it's clear, right? That you know what you should do, you just multiply them, right? So we can multiply the elements in this set, and what do we get? We get 4 to the power, how many numbers are co-prime to 15? That is Fn, right? And here it is 3, 3, 6, and 2, 8, right? Times this product, no, 1, 2, 4. This is a strange product, but it is a product. 8, 11, 13, 14. And but we know that this is the same thing as this product. I mean, modulo 15. Because that's what we have done. But then you can cancel. Now you can cancel. I mean, that's why we did all this. But then it worked out also because the remainders didn't go outside. Yeah. And the remainders won't go outside. Remainders will be distinct, but the remainders won't go outside. Because if you start with something which is co-prime and you take multiples with something which is co-prime, which are co-prime, how can you get something which has a GCD more than one? You cannot, right? Product of two co-prime numbers is co-prime. So it was clear already earlier, but then yeah, through the example. But then what do we know? We get this 4 to the power 8 is congruent to 1 mod 15. But what does all this mean? Well, it means that you can replace this thing by Fn. You can take that Fn, right? Fn many numbers which are co-prime to n and less than n. And this is a better theorem. Again, same proof will work. You take any a which is co-prime to n, you take all the numbers that are less than n and co-prime to n, you act by a on them, you hit them by a, multiply them by a, this permutation, and same thing will work. And obviously, when n is prime, then Fn is p minus 1. So we recover our earlier theorem. Yes. Uh-huh. Yes, exactly. So you're okay. So you're trying to find the numbers that are co-prime to n, and yes, so you have to prime factorize n, and you have to take the prime factors. Forget the multiple you're saying, right? The multiple, yeah, whatever. So even those prime, just worry about those prime factors, right? And you shouldn't get anything means basically you should, whatever numbers less than n you take, they should not have those prime factors. Right, their prime factorization, as you just said. Yes, that's right. That's right. But then, I mean, how do you get a better formula or whatever, right? Yeah, but your description is along the lines of something interesting, which maybe we'll work on that more, right? The power of prime, and maybe then you take two prime number with two prime factors and you try to find the answer, right? In terms of P1 and P2 or whatever, right? Formula, then we can see. Yeah, so that's why I've kept this Fn still like a black box. But so does everybody, yeah, understand this? I mean, we worked out the example, but it's a general thing. Okay. Yes. This is then this will be the end for today. Yes. Please go over it. I mean, I will go over it again with examples next time. This is not something that we do all the number theory in one day, but this is called Euler's theorem. So Euler came after Fermat, right? So he generalized Fermat's theorem. Obviously, now we have a language which makes all this easy, but this is Euler's theorem. It's called Euler's theorem, and yeah, and that's called Fermat's Little theorem. So yeah. So is this really okay with everyone? Please, yeah. Yeah, that when you take any number co-prime to n and you multiply it with itself, a suitable number of times, you get 1. And this is not a combinatorial factor. This is just a number theoretic fact. Because by combinatorics, you can prove that there is some power which will give you 1. That combinatorial Pigeonhole principle can prove. But what is that power? We are understanding that today. And this is really what number theory is, right? And yeah, so take more examples and try and so on. Yeah, and next time we will meet. And I will try to send some problems based on just simple applications of Fermat's theorem. Okay, little theorem. I think that's practice. Yeah, more and more practice. I mean, you will also find them in the books, whatever books you have, number theory books, yeah, whatever. But challenges and thrills is I will not suggest now because I don't know what kind of things are there. No, it is not there, at least here. It maybe is there. Anyways, forget about it. I will send some practice for this. Okay. Yes. So yeah, good. Like today we started with